Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Students, but anyway, I've known Mark for many years that way, and there's a crew of people who went from CMU to NASA Jet Propulsion Laboratory working on mobile rover technology, vision, and navigation. So we're going to hear about stuff that's up on Mars today.
Okay, thanks, Steve. So yeah, I'm Mark Maimon, and I worked on the flight software team for NASA's Mars rover missions. So that we have two rovers right now still on the surface of Mars, and they've both been up there for over a year. And we originally promised about 90 days of operations, but we're still going strong a year later. Things are going so well that actually this coming week we're planning to send up a new load of flight software. We're sending a new patch up to keep it going even better and make it easier to command. So I thought I'd talk today about what was involved in getting the rovers to drive themselves autonomously on the surface of Mars. I'll talk a little bit about the driving in general, but mostly focusing on the autonomous behavior. And the reason you want to be able to drive autonomously is we only get to talk to these things about once a day. So imagine sending out just one message saying, here's what I'd like you to do today, and then you have to wait 24 hours or 24 hours and 40 minutes, and then you get the results back and you get to see whether it did what you really wanted. So the more autonomous you can make it, the more you can accomplish in any given day. So just to give you some idea of what we're looking at, this is a picture of Mars. This is Gusev Crater, and I'll show you where it is on the planet, but basically you can see here some of the tracks left behind by the Spirit rover as it's driven through the plains of Mars. So you'll see a lot more pictures from Mars, and feel free to ask questions if you have along the way. So why are we going to Mars? Well, Mars is interesting because it looks a lot like Earth. It's smaller. Excuse me. It has only about a third the gravity of Earth, so it has less mass, less gravity, things weigh less. But we also thought we found from orbit evidence for past history of water on the planet. But we didn't have any way to confirm that. And so what we wanted to do was go there and actually look and see what we could confirm by looking in situ or on site with the instruments on the rovers. So the goal was to look for life or evidence of past life and try to understand the climate and also just understand the water history of the planet. Really, the purpose of the two rovers going there right now, we don't even have any sensors that could tell us if there were bacterial life forms, but what we have are sensors that tell us, was there water there, how long was it there, that kind of thing, so we can understand what the climate was like so that we can know whether the conditions were good for life in the past. So this is an elevation plot of the surface, and we've landed two rovers across the planet. So one of them landed here in the Meridiani Plains, and one inside the Gusev Crater. The picture you saw was taken inside the Gusev Crater. And when we send these things, we don't really know where we're going to end up very precisely, because the landing system is such that we have a landing ellipse error of about 200 kilometers. So we were actually very limited where we could land these things, because we're going to land using an airbag mechanism and bouncing when it hits the surface, and we needed to have some confidence that even within the region of 200 kilometers, there'd be nothing that would tear the bags or land inside a hole or land on too steep a slope or anything. So that kind of limited our choices, but we ended up narrowing it down to those two places. And you can see here one reason we wanted to go to Gusev Crater. Again, this is about 200 kilometers, so the diameter is about 300. It looks sort of like, not only is it a crater, but it also sort of looks like a river basin. So we thought this would be a good candidate place to go look for evidence of past water. And on the other side, we had, so this is the Meridiani area, and this is Gusev. It's not obvious from this picture, but this one was interesting from orbit because we saw evidence of a mineral called hematite, which is a kind of iron. And hematite on Earth usually forms in the presence of water. So our destinations were chosen mostly by the potential for yielding evidence of past water. And to get to the end of the story first, we found the evidence. At Opportunity Site, we found these rocks in this bedrock. So this is rock that's sort of native to the local region. It wasn't just placed there on the surface by a volcanic eruption or anything else. It came from that area. We found bedrock just 9 meters away from where we landed. So we lucked out quite a bit, actually. We landed inside a small crater, and we had the evidence we were looking for right there. And the thing that really proves that we have a past history of water is the chemistry. We find a lot of salts, sulfates there. And also the morphology, the layering you see here. If you have just rocks that accumulate as sedimentary rocks, they're usually flat layers. But if it accumulates in standing water, you'll see these wavy lines, intersecting wavy lines. And so based on that evidence in these rocks that were found in the bedrock, that's how the science team determined that there actually was water on the surface here. Now we lucked out. We found this very close by, just 9 meters away from where we landed. So within the first couple of weeks, we had initial evidence we were looking for. But this didn't tell us how long the water was there. Right? This tells us in some small-scale period at some time over the last 4 billion years there was something there, but you don't know really for how long it persisted. So we'd find out more later. Okay, so that's the end of the story. Let me back up to the beginning and talk about how we put these things together. So here's a picture of the Spirit and Opportunity rovers, and you can see the sense of scale here with the person in the background. These were designed to be robot geologists. So if you had a person, a human geologist, go and explore a site, you'd want to be able to look around. So we have cameras on a mast, and the mast is about eye level. It's 1.5 meters high. So we have the cameras there, so when we look at those images, it's what we would see if we were standing on the surface and looking down. And we're able to drive around. We have 6-wheel mobility we can drive. And you can see this scale change here. These rovers, compared to the one we sent 7 years ago, the Sojourner rover was part of the Pathfinder mission. And this one, in 3 months of operation, drove a total distance of about 100 meters. And we have done more than that in a single day now. So that's the kind of capability increase we have with this last mission. So what kind of parts go into making the robot geologist? Well, we have 4 cameras on the mast. There's 1 pair of cameras that are used for navigation and planning by humans on the ground. So when I say on the ground, I mean here on Earth. Humans will look at the pictures taken by these cameras. It's about a 45-degree field of view. And so we can move the mast around, so we take a panorama and merge those all together. And we use those to plan our motion for the next 10, 20 meters of driving in the nearby area. We also have high-resolution panoramic cameras with a much narrower field of view, about 16 degrees. And they also have color filters. So anytime you see a color picture from Mars, it was taken by the cameras on the mast here. And those are used almost exclusively by the science team for doing the color analysis and the spectral analysis of nearby rocks, and also for planning long-range drives, like 60 meters, 70 meters. We have a few more cameras. There's two on the front here. It's maybe hard to see, but there are 2 cameras here, and these have a very wide field of view. It's actually 180 degrees across the diagonal. So they see everything in front of the rover, including its own wheels. So it was interesting when we first started testing these things, when it was looking for an obstacle in front of it, it found 2 big obstacles really close by. But we were able to deal with that. So the other parts that contribute to the system, we don't have any bumpers or contact sensors. It was something we all wanted to have, but when you're sending something into space, you need to limit the number of components and motors and moving parts, because anything you put can just go wrong, and you don't want to lose the system because of one failed component. So there's a real push to add as few sensors as possible just to keep the system simpler. We also have, I won't be talking much about this today, but we also have an instrument arm, which we call the IDD, because NASA doesn't like to use acronyms that make sense. They could have called it the Autonomous Rover Manipulator, which would be an arm, but instead it's the Instrument Deployment Device. And that has the majority of the science equipment is on the end of that device. So we have 2 spectrometers, we have a close-up camera that takes microscopic images, and we have the grinding tool to dust off the surface. And that's the rock abrasion tool, or the RAT, And so you'll hear people talking about after we've done a grind operation, you have little rat droppings all around the target. So we also have on board gyros and accelerometers that measure the accelerometers tell you where gravity is, and the gyros tell you how you're drifting as you're moving or just sitting still using the arm over time. And those are very good. They work really well to tell us what our heading is, but they don't tell us where we're positioned. And that causes some problems that I'll talk about a little bit later. And as far as actually getting around, we have a 6-wheel, what's called the rocker bogie suspension system. It's a 6-wheel system that has a built-in averaging so that if one wheel climbs over a rock, the whole vehicle doesn't tilt by that much. It gets sort of averaged out among all the other wheels. And that keeps the whole system overall from tipping over. So there's a lot of vision people here, so I thought I'd just give a quick summary of the cameras. When we launched the spacecraft, we had 10 cameras on board. So I told you about 9. There's 4 on the mast, 4 on the body, and 1 on the arm. And there's a 10th one that was used on the back shell when it was coming through the atmosphere. We took 3 pictures of the ground on the way down as we're plummeting through the air, slowing down from supersonic speed. And those pictures were used to estimate how fast you're moving horizontally. And based on those pictures and an automatic assessment of what our horizontal speed was, we decided whether or not to fire the retro rockets. And this is something that had to be decided on board because there was no time to send the images back to Earth and relay the signal back. It takes about 8 minutes minimum for a signal to go back and forth between Earth and Mars. And depending on where the planets are, it could be as long as 40 minutes. So that camera worked really well. It took only 3 pictures, but there were 3 important pictures on both of them. The first one actually used that information to fire the retro rockets and slow down. If it hadn't, it might have hit and bounced, excuse me, and actually torn the airbags and damaged the whole system. So we were happy to have the cameras there tell us that. We didn't need it in the second time, but it was good insurance anyway. And I already told you about where the other ones are. So these are small by current standards. I mean, it's only a 1 megapixel CCD. But we still get some nice results out of it because we can have very precise control over how we actuate the pan tilt head. So talking about driving, there's 3 kinds of modes that we think about when we're planning a drive. We have either a long traverse where we're trying to get to some long-range goal. And so for instance, the Spirit rover landed and found some nice stuff, but really there was no evidence for water within about 3 kilometers of where we landed. We had to drive 3 kilometers away to get to some hills, the Columbia Hills, before we actually had that evidence. So for a long traverse, you really don't care where you end up. You just want to keep driving as much as possible. And in that mode, if the rover is driving itself, it can go about 35 meters per hour. So that's about, a little more than 100 feet per hour, or about a football field in one day, because the rovers are powered by the sun, and there's limited power available, so we can only drive for about 2 to 4 hours at most in any one day. Most of our driving is of this other kind, though, where we see something interesting nearby, say about 10 meters away, and you want to approach it. You want to get it close to the work volume of the arm, so you can do some close-up sampling with it. And then there's final fine positioning. When you get within a meter or 2 of where you want to be, but you really have limited workspace. The arm only works within about a 50, 60 centimeter disk, so you really have to move it into the right position to be able to use the other sensors. And when we're driving in all these phases, this one, we typically do use the autonomous driving, where we're looking ahead and letting the rover choose its own path. But here we found that our system worked very well on flat ground. We didn't need to have the extra safety feature of having it look at the terrain and plan ahead whether it would hit anything. So we ended up doing most of these with just direct blind driving commands, where we'd tell the rover, like, drive forward 2 meters, turn right, drive forward 1 meter. And these are the kind of basic commands that we had. We could just tell it, drive along an arc or drive straight for some distance, turn in place by some amount. Or we would tell it that we want you to go to this point in space. So rather than say, go to that rock over there, what that rock looks like, we measure it in our cameras, in the stereo camera images, and say, we want you to go to the rock that's 10.2 meters this way and 3.4 meters that way. And when we do it in this mode, this is where the rover will try to get to this point, and it will decide for itself where there are obstacles in the middle and avoid them along the way. I'll just try to go through this pretty quickly, but because this was designed by engineers for engineers, we have a lot of ways to control this thing at many different levels. We can control the motors directly, just saying, you know, spin the wheel this many times, without caring about what you encounter or how you'll actually drive. And we've used that, for example, to dig trenches. We don't have any digging tool on the arm, but our wheels, if we spin the wheels in place, we can dig down that way and excavate some soil. Then we can just do blind driving, where we just say, you know, drive forward 2 meters. And that just tells it how many times to spin the wheels and stop. But usually we do that with the IMU to tell us what our heading change is. And then there's another mode where we have guarded motion, where we request one particular path. We tell the rover, we want you to drive this way, but only do it if it's safe. So in that case, it'll use its cameras, using the procedures I'll tell you about shortly, to see if it's going to be safe ahead of it, and only follow that one path if it's safe. That's different than the other mode, hazard avoidance, where it not only looks, but it's also allowed to choose for itself which way to go. Because sometimes we're so limited in power that we're only have enough power to do a certain kind of drive. So even if the rover could figure out how to get around it, we don't want to spend the time or the power or resources to let it do that. And finally, we haven't used this very often, but we have actually used this once very recently, so I need to update this. There's a chance for letting the rover choose its own target, where you tell it, I think there's some rock that's interesting nearby, please find it for me and turn toward it and drive toward it. So that we have used it only once. We've mostly gotten by with these other modes. Yes?
A couple questions. Is there enough of a magnetic field on Mars to use a compass, and are the accelerometers good enough for position?
Okay, so is there a strong enough magnetic field to allow a compass? And no, there isn't. That's why we had to use some other mechanism. What we usually do is we use the mast cameras to find the sun. So if you can tell where the sun is and you know what time of day it is, that plus the gravity vector is enough to tell you what your attitude is. And the second question was?
Are the accelerometers good enough to double integrate and find position?
Right, can we doubly integrate the accelerometers to get position? And the answer is no. They're too noisy for that. So typically when we drive, we only use the wheel odometry, counting wheel rotations to estimate our distance traveled. But I will talk about the other technology we use for that, which is to use images, to update our position knowledge. Yes?
I thought if you have a gyro and are standing still on a rotating planet, you can find out which way is north, because the gyro is coupled to the planet, and after a while it will point north.
Well,
you didn't have the kind of that, or you didn't have the kind of gyro?
Yeah, we didn't have enough. You probably need to integrate for a longer period, and that wasn't something we're willing to do, stop for that long a period in between every driving step. We found it was just faster to look for the sun and track it that way. Okay, so talking about the long-range driving, what kind of capability do we have? And as it turns out, with the Mars rovers, in benign terrain, when it knows that it's safe, we can still drive, I was saying earlier, about 35 meters an hour, so in 3-4 hours we'll get 100 meters of driving. And that's pretty good. That's the whole previous mission in one day. And that's with all the safety features turned on. Now, you guys, I'm sure, know something about problems with releasing software and working with beta versions and all this. And so we actually drove our primary mission, the first 3 months of operations, with the beta version of the mobility software. I had done a lot more testing and field testing and some changes to make it able to be more adaptable. But the mission managers didn't want to risk changing anything once we landed. So we had to go for the first 3 months without it. So at that time, our driving speed was much less. It was about 9 meters per hour with the autonomous software. And it was only after we sent an upload after 3 months of operation, after 90 days, then you can see the speed cranked up a lot. So fortunately, we've had that mode for much more, and that's what let us get to the Columbia Hills, which are 3 kilometers from where we landed Our goal for the mission was only to drive about 600 meters total. So I'm very happy we were able to, meet the scientists' goals by getting to the far target that had the science results we needed. Yes?
And why is there so much variance?
Why is there so much variance? Because this is the actual linear distance accomplished.
Some days they were at an interesting place and didn't decide not to move.
Well, yeah, some days they were blocked by obstacles and couldn't go and had to work out a way to go around it. So there's a difference between just a straight line drive and one that had to avoid the obstacle along the way. Okay, so these different ways of driving are implemented using these basic technologies. We have ways of detecting problems on the vehicle, hazards, reactively. So, the vehicle is measuring its tilt, and if it's too far tilted, it'll just stop driving anymore and error out and just call home and ask for help. Then there's predictive hazard detection, where it uses the cameras to look ahead and predict what is going to happen to it if it drives in this way. And another technology we call visual odometry. So instead of just counting the wheel rotations, you take pictures before and after a short drive segment, and you can track features and use the feature tracking to estimate what really happened. Now, that's not something that we actually baselined for the mission, but we managed to get it in there anyway, and we've been using it all the time now as we've been driving in these craters where we're tilted at 24 degrees all the time, driving on slopes, slipping toward dangerous rocks. So it's been very handy having that more recently. So the kinds of reactive hazard detection we have, I mentioned the tilt check. Anytime we have a motor stall, draws too much current, that'll stop the drive. We can also choose it so that if the angles on the legs, the axle, the bogie and rocker components, if they get out of bounds, we can stop a drive. We'll also check for other possibilities, like if we're doing something like using the arm, we don't want to drive and drag the arm out there. So the software will automatically check for these kinds of conditions. The arm has to be stowed. If we do a check looking ahead, if the path is not safe, or if none of the possible paths around it is safe, it'll just stop. So we have these kinds of things that find when we're already in a problem and when we're predicting we're going to have a problem. So let me talk a bit about the predictive hazard detection. This is where we use the cameras to look ahead, and we use stereo vision image processing, and we can use any pair of cameras on the vehicle. We always use the front has cams, the body-mounted wide field of view cameras, and the rear-mounted field of view cameras on Spirit, and we can use the nav cams on Opportunity. They give us range data that let us understand the environment. I'll show you a video shortly that explains that. And we can also do our position estimation using visual odometry. And once we detect the information in stereo, then we do a kind of assessment of what's going on around the vehicle. We're looking for potential hazards like a big step there, or a big rock, or a big ditch, or too high of a tilt, or too much roughness, if it's just generally too rocky to get through. And any of those will cause us to avoid that area. So let me show you a quick video here. So we'd like it to drive.
Class, today's lesson is autonomous waypoint navigation in natural terrain. This is your designated goal location. First, watch this video to learn how it's done.
Okay, so I'll just talk to the video here. This is what happens when the rover is doing predictive hazard avoidance. It's using its cameras to look ahead and plan how it should drive the step ahead. So we're typically moving at a very slow speed. The rover mechanically can move at about 5 centimeters per second, about 2 inches per second. But it moves slower than that when we're doing this work because we have to stop and think about it before we can keep driving. So we'll drive at 2 inches per second until we reach the end of one small segment, look at the terrain, choose a new path, and then actually start driving. So what happens when you get to a new spot? Well, we end our drive segment and stop and take a pair of pictures. And then we'll do automatic stereo image processing on those pictures. So the rover will take the two scenes simultaneously. And there's no flash, really, just to give you the idea. It's taking a picture. And we automatically compare the two images and correlate each pixel by pixel to find out how far away each one is. So basically, when you find points that match between the two images, you get two rays in space. Where the rays intersect, that's the distance to the target. So we're doing simple triangulation to find each point. Now, the Sojourner rover 7 years ago had a similar capability, but it could only find 20 points per image pair because of its slow processor. And we typically find 16,000 points, 20,000 points in one set of cameras, and even 50,000 points in the other set of cameras. Yes?
What is the processor and speed?
We're using a RAD 6000 PowerPC derivative, and it's a 20 megahertz CPU, which is 200 times faster than the previous rover's CPU. And so as we go, we're looking at the terrain, and we assign a color coding on how safe it is. Green means it's perfectly safe, go there as much as you like. Yellow is still okay, but a little worse. And red is bad. So we'll do an analysis by fitting a whole rover-sized disk to a plane and looking at the residuals of the plane fit to give us some idea of how safe it is to be at each point. So then as we drive, we make sure and stay out of any red zone. But we're always trying to get towards some goal, so we'll get arbitrarily close to the red zone. And the way it chooses a path is to look at all possible paths ahead of it. And it can look at curved paths and turning in place and then driving straight. And each path is assigned some vote as to how safe it is. And then what it'll do is it'll pick the safest path that moves it toward its goal. So here we've done all that work. That takes about 2 minutes on this processor. We take an image, find the points it represents, assign it a safety analysis, choose the next path to go. And we usually only drive about half a meter or 60 centimeters per step, and then but we can go as far as 2 meters before taking a new image. Our image data and our positioning is good enough to let us go about 2 meters before we have to take another one. Yeah?
How long do you plan ahead?
How long do we plan ahead?
So you drive 50 centimeters, but how long is the plan that you...
Yeah, plan is about 3 meters. So we're looking as far ahead as 3 meters or whatever the remaining distance is to our goal, whichever is shorter. And hopefully this doesn't happen. It hasn't yet, so we've been up there for 13 months now. Okay. Okay, so that was an animation showing you what goes on, and this is what we really see. Here's one picture of a stereo pair we got from Mars, and you can actually see here the little logo here is actually the result of having used our rat on the rock to brush it off and brush away the dust so we can measure what's inside the rock. But this picture is presented here both in terms of how far away each point is from the vehicle. So red is close, blue is far away, and yellow is sort of mid-range. And here is the elevation. So you can see that the rock is tall because you can see we're measuring the height of it over here. And that's the kind of data that we get back from every image. And we usually get, as I was saying, tens of thousands of range points. So the way it works is to take the picture, do that analysis, and we have filters that throw out any sort of noise in the image. We don't always get good data everywhere, but we're smart enough to throw away the images. And anything that's green is assumed to be good, and that's what we look at the elevation. And we color the map here. So this is a picture that we took on Spirit after the rover drivers had sent it a certain distance, they drove 15 meters blind, and they wanted it to drive straight ahead. But if it had followed their command, it would have driven into this rock, it's tall enough, it's about a wheel size. And that's enough that it might have gotten caught on it. Fortunately, we ran this code, and so instead of getting caught on it, the rover noticed it, and it actually chose to back away. This is the before, and that's the after. Saw this picture, and it chose to back off from the rock first and drove around the side in order to get to where it was going. So also, I already mentioned this, but in addition to letting the rover choose, we can also tell it just go this way and only go if it's safe. And then this capability we put in, roboticists love this stuff because we like to make the rover think for itself and make it smart about choosing where it's going to go. So we added the capability to find something interesting nearby. We're already finding where obstacles are, right? We know where the bad things are. We usually try and avoid them. But what if you wanted to find some rock and drive toward it? So we just turned it around and used the same map to find a target and let us turn toward it. So here's an example. We didn't tell it anything about the scene. We just said turn toward the nearest rock, and you can see it centered on it. And we did actually do that on Opportunity recently, but we kind of cheated because there was only one rock in the neighborhood. But it did find it and turn toward it. So the other kind of autonomous capability we had is to estimate the motion to compensate for any slip while you're driving. And that works in a similar way. It finds features in the scene, tracks them across different frames, and matches them up, and that gives us the transformation from where we started to where we ended. And this has been really, really good when you're driving on steep slopes and inside craters. And what it does, this is a run from our test bed on Earth. You can see it's tracking the flow, the motion of the feature across the scene as it's driving. And the benefit here is that the system had a design spec that we wanted to be able to drive and stay within our desired position estimate by 10%. So we wanted to know where we were to within plus or minus 10%. And that's what this line represents. This purple here is the error we actually saw in the test bed when we drove over a lot of rocks. So we were sort of losing our knowledge as we're driving over the rocks. But by running this processing on the images we were getting, we actually were able to bound the error quite a bit. We kept it down to about 1 or 2%. Yes?
I'm curious about the wheel slip. It seems like since you have 6 wheels, you could deduce the amount of slip on any given wheel and do almost the same thing you're doing with your visual odometry just by keeping track of slippage in each of the wheels.
So you're saying, couldn't we keep track of slippage in each wheel independently to know what our slip was and compensate for it that way? You're right. There are research programs going on that have done similar things to that to try to help compensate for driving. But really, that's never a precise thing. What you can do is you can measure the current that's being drawn, so you know how hard it is to drive in this location. But you never know for sure which part's slipping, and especially if you're driving sideways on a slope. Your forward motion is always going to be fine, but you're still sliding downhill, and you don't know it. So having the visual system there is a very useful fallback, and it's done a great job for us of measuring our slip in all directions. Yes?
So this visual processing, is that done on Earth, or?
No, that's on the rover.
On the rover.
Okay. Again, since we only get to talk to it once a day, there's always a trade-off. If we think on Earth that the terrain is good enough and safe enough that we don't need to worry about it, we don't use this software because it takes a couple of minutes to do its processing. But when the desire is to really get to a point you want to be at, it's much less expensive overall to spend longer thinking about it and make sure you're there rather than waste a few days having to compensate. Because early in the mission, they weren't using the software, and we did waste days getting to places, even just a few meters away, because we'd have to drive over soil and rock, and you can't predict how much you're going to slip. And now that we've been using this, we've had drives, even on the crater rim at 24 degrees, driving on the rim, driving to a point 8 meters away, 25 feet away. We got it directly into the work volume we needed in one shot. And we'd never be able to do that if we weren't using the image processing.
Are there no LiDAR sensors capable, time-of-flight sensors capable of giving you more accurate range?
Okay, could LiDAR sensors give us better data? Probably. And at least more quickly they could give us the data. But the thing is, having a LiDAR sensor would mean you need more power to use it and more moving parts, because typically they're on scanning moving platform, and that's always a problem in space. So the nice thing about this approach is it uses fixed mounted cameras that were already there for other reasons. But you're right, that is a viable solution if we had the extra power to support it. Yes?
When you're driving autonomously, you're taking pictures, right?
Right.
Like every 15 centimeters. Do you merge those pictures, and if you do you use this odometry to merge the pictures into a plan?
Okay. As we're driving, do we merge the pictures, and do we use this odometry to merge the pictures when we're driving autonomously, trying to find a safe path? We could. Software supports that. But if it's 2 minutes to do each separate piece of processing, it's 4 or 5 minutes to do both together. And so they typically haven't wanted to spend the time that way. So we usually do one or the other, not both together. And also, the thing that actually allowed us to speed up our driving is we don't always take a picture every 50 centimeters. If the rover decides if every path around it is safe, so if it hasn't reached any potentially dangerous area, it'll keep driving for up to 2 meters before it stops and takes another picture. That's only for the hazard avoidance. For this thing, you have to do the tracking by nearby frames all the time. Yes?
When you shoot pictures of the ground to find where you are, isn't it exactly the same problem solved with optical mice?
Isn't it the same problem that optical mice solve for tracking things?
They look what's underneath them, and they know how far my finger is moved.
Well, we don't actually have a camera underneath the rover.
Yeah.
We're looking off to the side. It's a similar kind of problem, but I don't know all the technologies that implement the optical mice tracking. But anyone know if it's feature-based or?
So it's on any surface?
Any surface. Well, our stuff works on any natural surface that has sufficient texture to track, and I'm sure the optical mice is similar. Yes?
My question kind of goes back to the beginning. Did you guys consider using a humanoid type of robot instead of, one with wheels? So if your humanoid would fall down, you can always get up again and that stuff. So,
right.
Yeah.
So did we consider using a humanoid instead of a wheeled vehicle, like a legged vehicle? That was considered early on, but so far we have the heritage showing us that wheels work on the Sojourner rover. And it's a really tough sell at NASA to do anything new. So there are certainly people working on research projects to do legged locomotion and all, but in general, wheels let you use less power. You don't have to, you don't have the gate for doing that. You're just rotating in place. They generally use less power, and that's a big plus for a space mission. So that's a large reason. But frankly, if we had a good argument for it, it would be reasonable to consider the legged locomotion. So let me just give you a feeling for the visual odometry here. This is an animation that shows one drive inside a big crater. And what you'll see is you'll see 2 rovers, one that plots the path it actually took as measured by the visual odometry system, and one that plots the position it would have thought it was at if it weren't keeping track. So it really is downhill here, but if it weren't doing the image tracking, it would have thought it's following this path up top. You can see it makes a huge difference right away, and for most of our driving, we tried to go either up or cross slope so that we could understand what was happening, but you can see that introduces a lot of slip. We're already more than a rover away from where we would have thought we were. And by the end, we're several rovers apart. This tool, by the way, is something that we use every day to visualize our not only what we did the previous day, but also to plan the next day's activity. We get a 3D model of the terrain nearby, and we can drive the rover over the terrain virtually, and that ends up creating the commands that can be sent to the rover when we run in that simulation. Okay, so here are a couple pictures from Mars. This was the first time we used the visual odometry, and you can see it's finding all these features in the rocks nearby. And this is what processing done by the robot at Mars. And we did this so that we could get a closer look at this part of the rock that we drilled Because when we drill it, we can't see it with the cameras on top. We have to back off before we can take a picture. So in backing off, we're going to slip some unknown amounts. We want to make sure we can see it. And you can see that the target ended up dead center in the image. So what was really necessary for this mission, for most space missions, the mantra is don't make it flexible. Build it one way so that we can test it and know that it works that way and we don't have any other things to worry about. But for this part of the system, we had to do just the opposite because we couldn't predict what kind of terrain we would see. And in fact, after we landed, I had done almost all the development testing using low-resolution images, 128 by 128 pixels. That turned out not to be enough. When we actually saw the terrain on Mars, we could have gotten away with it for Spirit, but the maps that it generated would have been very noisy and very had too many obstacles. But it worked much better at a higher resolution. And then for Opportunity, you'll see pictures later that show the terrain there is so fine, it's just very fine-grained sand. When you look at it in cameras with that resolution, you just see gray. Not even changes, just 128, 128, 128 pixels. So you can't do anything with that. So fortunately, we had enough flexibility in the design that we were able to accomplish that. So I'm done with the words now. I'll just run through some pictures and things, show you some pictures from Mars and before Mars. So before you go to Mars, you got to know something about your cameras. And we use a calibration procedure that looks at these dots. So we measure the dots. We measure where they are in the real world using theodolites, total station. And fortunately, even though we do the calibration on Earth, things survived the launch and the landing just fine. And we were able to use the same camera models even after we landed on Mars. And we built an indoor test area that was sort of to give us a fake Martian environment. So we have the red soil and different rocks. And this is sort of interesting. We found that our algorithm for doing the stereo imaging is very good at natural terrain, but not very good with man-made things. So in particular, the white walls with the power strips, these horizontal lines all around it, you never quite get the registration perfect with the camera model. So it's comparing two horizontal lines that are a little bit different, and it ends up matching them in not quite the right place. So while I was testing this thing, the rover would drive and suddenly stop and turn away from nothing. And I didn't know what was going on. I looked into it, and it turned out it was seeing power strips as spears coming out from the walls. So we were able to deal with that in software, but we also put up this camouflage just to give it a little help there. And we also made sure not to do much autonomous driving around the lander, which is the other source of straight lines you'll find on Mars. And so this is sort of a timeline. This was in January 2003. The rovers launched in the summer of 2003 and landed in January 2004. So January 2003 was when we had our first successful autonomous driving around a rock. I basically started it here, told it to go here, and didn't tell it anything else. So it was taking pictures, and it saw the rock and chose on its own to steer around it. So more calibration. This was of the actual flight vehicle. I didn't get to play with the actual vehicles very much. In fact, I only got to use them a couple times before we launched. Instead, I had an engineering model to work with inside the sandbox. But I was involved with calibrating the cameras and making sure everything worked in the clean room areas. So we also ran some very basic mobility tests. But of course, because we're sending these things to Mars, we couldn't put them into our sandbox. We couldn't risk contaminating them before we sent them to Mars. So we had to do very basic testing inside clean room areas. And there are all kinds of hazards when you're working at a facility in Florida near the Everglades. Fortunately, rovers didn't have to avoid that one, but we did. And we did get to do some field testing, but not till after we launched the rovers. Then we got to actually take the engineering models and go into the desert, into Edwards Air Force Base, and drove in some areas there to give us some practice outside. And we built an area at JPL. JPL's in Pasadena, near LA. And we built an area we call Mars Land up on top of the hill here. And this was the longest open area we could do our driving testing in, yes.
What's this long cable the rover is trailing?
Yeah, what is the long cable? On our engineering model, we didn't want to worry about power issues and powering it by the sun or anything, so we just used a connector for power, and so we also used it for Ethernet just because we could. But this is the area. You can see we built up small hills and small boulders to do some of our testing. And then one day I finally got a chance in December of '03. This is like a month before we're landing. We got a chance to use this area, and I decided to try telling it to drive off a cliff just to see what would happen, right? The goal was off in nowhere, and right up when we're about to start this test, CNN showed up to get some footage. So they hung around for the test, and lucky for me, the rover got this far, saw what was going to happen, backed off, and then drove along the edge. So it didn't actually fall off, so everyone was happy. And in January '04, we landed on the surface. So these were the first kinds of pictures we saw from Spirit's landing site. Anytime you see a lot of rocks out on the flat ground, that's the first rover, Spirit's site. And this is the second rover, Opportunity. Its area has this fine-grained sand just everywhere, and it's just really difficult for image processing. But this was the first picture we had from first wheels on soil. We gave it a command to drive 3 meters off of the landing platform. You can see the tracks here. People just studied this image like crazy to see if we had done anything wrong or any potential problems, but everything worked really well. And to give you an idea of what we're doing here, we landed in this area, and we promised NASA we'd drive 600 meters. So we promised we'd go about this far. And we did that in the first 90 days. We went to about here. But really, in all of this driving up to here, the science team found no conclusive evidence for past history of water. Even though we're in this supposed lake basin, they just couldn't find anything in the rocks. It wasn't until we drove all the way over here, 3 kilometers away, that they finally got some bedrock here that showed a similar kind of sulfate content and all that. So it took, beyond the extended mission, going much farther than we had promised to be able to do it. So mobility is good. And to give you some idea of how much it was used, the blue here is the blind driving. This is all in meters. And on the bottom here you see sol or day, a Martian day. We call it a sol to distinguish. And anything in blue is distance we drove blind. Red is distance we drove autonomously, avoiding obstacles. And the green is where we drove using the visual odometry, doing our position estimation. And one of these gaps here is because that's when Mars went behind the sun. And I was rooting for just telling it to drive 5 kilometers and see what happened 2 weeks later, but we didn't do that. We just let it stay in one place. Some more pictures. One of the first long drives, the rover was sent to go 40 meters. We could only see very well out to about 12 meters, and it stopped short. So I was sitting on the station thinking, oh no, what's the problem? What did I do wrong? And in fact, it had stopped right where they wanted to be, at the target, the pile of rocks, that they had misestimated the distance to it because we didn't have the high-res stereo images going out there. So the rover did the right thing. And you can see here, this is just a few sols into it, looking back on some of the tracks. And if you look closely, there's the lander. So that's about 50 meters behind it at this point. But that's the last we're going to see of it. So along the way, as it's driving, you can see here, they would have driven it blind up to about here and then turned on the autonomous driving. And that's where it made its own decision. It saw this rock and said, whoop, I'm going to steer around that one. And some more, just another case of the same thing, driving along, going toward its goal, and it's blocked by this pit with rocks and a low ditch. And it saw that on its own and decided to swerve around it. And another time, again, from about 20 meters away and off at an oblique angle, the people planning the drive saw these rocks and said, we really want to go straight through these rocks because there are more on either side. But they thought it was about 4 meters apart, and the rover is 2.6 meters, or about 8 feet wide. and they thought it was just wide enough for it to go. But it turned out that these rocks were really about 2.7, 2.6 something meters apart, which is right on the edge. So here's a track of the course it took. It drove blind out some distance, then they turned on the autonomous driving, and it kept trying to go through there. It tried to go forward, tried to back up, turned around, tried to find a way around it. Couldn't make it. This was the first picture I saw that day. And I was very happy it was still in front of the rover, not under the rover. But this is just a case showing you that even though the humans thought it would have been able to go through there, they had misestimated things, and so the rover kept it safe, even though people didn't have the right numbers there. And another case where this big rock wasn't visible from the planning images because it's about 60 meters from where we started. But when we stopped driving, we hit our time limit, turned to a certain heading to communicate, and then normally they drive forward another meter just so they can see a before and after shot. But fortunately, the rover stopped itself from driving into this. And we have limited bandwidth coming back from Mars, so we don't get to see all the pictures it takes. But one time, somebody made a mistake or something, and I got to see all the images it took on one of its autonomous drives. So this is a plot of that. You can see here it's found a rock, and it's backing off away from it, and now it's working out a way to drive off to the side. So this is the kind of thing kind of processing that was going on in the vehicle as we were driving autonomously. I can show you another view of that. This is that same information, but plotted. This is a virtual plot. This is playing back the whole day's drive in the terrain model. So that's that same drive that you just saw. And so it started off down here, drove blind there, and then they're driving autonomously. And that's the rock that it saw and drove around to the side. Okay, so, right. All right, just catching up here. Okay. Now, there are some kinds of hazards that we don't... Oh, sorry, Steve?
Now that you've had this much experience with the rover, are you happy with the design of the wheels and the mobility platform underneath?
You are the perfect straight man, because the question is, am I happy with the design of the mobility and the wheels now that we have all this experience? And if you look here, this is pretty far into it. We've been driving over a year, but at one point we're driving and we got a rock stuck in one of these wheels, one of these open wheels. Just a little potato-sized rock. And it's not a hazard by the definition we use. We're looking for 20-centimeter tall hazards. That's not a hazard. It wasn't even visible. It was underground. But we were doing so much churning up of the soil here, it came loose and got wedged in there. And that took us a week to do different maneuvers and try and shake it loose. Finally it did come out, and it only actually stalled us once, but we didn't want to let it stall us again, so we slowed down. So, no, we're not happy about that. There are other things we'd like to do differently. But what I am happy about is that overall the position estimation worked really, really well. The control of the motors and the precision with which we measured it gave us about 2%, 3% error in position when we're driving on the flat ground, even over kilometer scale drives. So that part worked really well. The rocker bogie suspension is reasonable for climbing over things like this. But it turns out now that we're into a whole new phase of the mission that we never planned for, things come up like we find that we really wish we could tilt the solar panels to face toward the sun, and we can't. And we even tried tricks to get the rover to sit up on its hind legs or something to aim toward the sun, and even that's hard because the stupid suspension averages everything out. So, now for the extended mission, it'd be nice to have some of these more capabilities, but overall it's worked out pretty well to start. There is another rover mission being planned And for that, they're going to revisit all these things and hopefully come up with better solutions. Yes?
You have a couple of rovers.
We do.
Right, but if they were near each other, could the fleet sort of take pictures of what the obstacles are that the other ones can't see, and the whole thing could move faster?
Okay, so if we had several rovers in one place, could they take pictures of the obstacles and be able to move faster that way? If we had several rovers, we have a lot of interesting things, like you could do localization, figure out where one rover is just by not moving one, moving the other, finding it with the other one's cameras. That kind of stuff would be useful. As far as finding obstacles, we do pretty well with this kind of approach. The one thing I would like to do is be able to see more from higher up. Like having the cameras on the body very close to the ground, we can't see over obstacles, means there's a whole swath of unknown area behind an obstacle at first.
But if you had two from some wide angle?
Yeah, so that might be helpful, but then the registration problem is really challenging. I avoided trying to register things in 3D, and instead I only overlay the idea of whether it's safe or not. So that gets overlaid, but the 3D analysis is done only within one image pair from one location. It would be very difficult to do the same kind of terrain assessment. Yeah?
This is a question about the mission, not about the rovers. What evidence is there that water is actually necessary for life?
So what evidence is there that water is necessary for life? And there's none. It's just that that's what we're so familiar with here, that is a strong candidate. If you're going to choose what to explore next, you try and do it in a way to maximize your potential return. So the science team had decided for this mission, and these missions, that our best chance was to look for where there used to be water. That would most likely give us the past evidence. There's no guarantee. Okay, so that was Spirit's Drive, and here's where we are now. After driving 3 kilometers, we ended up at these hills. And now we're driving very slowly, but we're moving up here. Right now we're on the ridge in this area. And in the next couple weeks, we should see a whole new panorama of an area we've never seen before on the other side of these mountains. That should be coming up very soon. And I don't know where we're going after that. We may try to go to the very, very top. We're going just to a small lookout down here. But that'll depend on what we see. And this is also something that makes this mission different than all of NASA's other missions, because except for the Sojourner rover driving around, typically a mission is planned, any mission operation is planned weeks or months in advance. You know you're going to be flying by Titan in 7 years, so you spend a few years meeting and planning it and adjusting your trajectory. But we have to replan every single day based on new data, and often on partial data. So it's been very interesting for the people who've worked on other flight missions. It's total change for them to adapt to this kind of planning. Just a DEM of this area to show you what kind of elevation we're looking at. And this is a tilt history of the Spirit rover. So we started out, we landed, and we drove off the lander, pretty high tilt coming off the edge there. Then we kept it pretty flat. And only now that we're climbing into the hills, you see we're getting into this 20-degree tilt regimen. What's the design limit? The rover will probably flip over at about 45 degrees. So we try not to go much above 30. And this is a nice picture. This is an after picture, okay? I'll show you a close-up shortly, but basically we landed around here, drove up here, and if you look closely, you can actually see tracks. There's rover tracks on the surface of Mars, all the way down to the hills here. I'll show it to you in 3 pieces. This piece, then the middle, then the end piece. So we were really pleasantly surprised to be able to see this in the images. This is from the Mars Global Surveyor orbiter. It's been in orbit for 7 years, since the same time the Sojourner rover landed. So this is where we landed. You can see the lander here. That's part of the vehicle, the back shell, the parachute. Unfortunately, we didn't get a chance to look at that, but we started off going to this crater, and the scientists decided that's not interesting. Once we got up close and saw inside, they didn't see any bedrock outcrops, so they just skipped it, and we just started driving down to the Columbia Hills. Down, 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 down. Down, 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 down. And finally now we're driving right about here. So we haven't covered that much horizontal distance since we got here, but we're climbing vertically, and it's been a real challenge. This is where we dug up that potato rock that got stuck in the wheel. And we're slipping a lot, so we're using the visual odometry all the time and a lot of things. And what's next is after we look over this region down into here, maybe we'll climb over here, go into this way. We don't know yet. It'll depend on what we see from the rover's cameras. So on the other side of the planet, Opportunity landed, and we got these images back. And this is what I meant about gray. You can see a little bit of texture here. This is where the airbags bounced on the soil. You can see the airbag tracks. But down here, at the compression ratio we were using, there was just nothing in the picture. No image processing could deal with this. So we had to reduce the number of images and crank up the resolution, use less compression in order to be able to get 3D information. Yeah?
So where did you take the last picture from? It seems like it's all the way from the top.
Yeah, where did we take this picture from? Well, it's not from orbit. This is from the mast camera, which you can pan and tilt and look down. It's looking down at itself. So what's missing here in the middle is the white camera body, because that's what's not shown, but it's just taking that from up there, and then it's projected, from a higher location. This is another after picture, although this was taken about 8 months ago, so it doesn't show the whole tracks, but we landed in here in a hole-in-one. There's just a few craters in the area, and we ended up landing down here. You can see the after effects of the thrusters to slow it down, and then bouncing into this crater. And that's where we spent the first 2 months. And we drove out here into this much bigger crater. This is about 140 meters across, more than a football field across. And we spent 6 months inside here. And we've just recently left and driven down past our heat shield, and we're trying to go 5 kilometers to the south now. That's our next goal, is to go. We're basically going to double our whole mission driving so far if we make it to our next goal. And you can see here, this is the driving plot. Mostly we did a lot of blind driving. Occasionally we used the hazard avoidance, but there aren't that many hazards. It's a flat plane, so they didn't feel a need for it. And a lot of the visual odometry inside the crater. And this is some of the terrain. And you can see here we dug a trench with the wheels, excavated some of this with the wheels so we could get a close look with the microscopic imager. That's actually a microscopic image projected into there. It just doesn't show up very big. And you can see some of the tracks here. And we have used the hazard avoidance stuff. Even though there aren't rocks, there are ditches. So this ditch here shows up as an obstacle in the rover's onboard map. And we did get all these images down from this autonomous drive, and you can see these are the images it chose to evaluate, that it had to evaluate its drive when it was driving 85 meters across the open ground. And mostly it's just ripples of sand. But occasionally, as it's driving, amongst the ripples, you'll see a white rock appear here. And we've actually haven't spent the time to look at that because the science team has always had other goals, but we may stop in the future and see some of those. We're seeing more of them now as we're driving farther south. There's one. There's more stuff here. So this is where we spent 6 months exploring Endurance Crater. And we drove in here and we saw these foreboding cliffs, and we thought, we're never going to get there. The science team really wanted to get there, but we're never going to get there. Well, we almost got there. You'll see a much closer up view shortly. But this has been really the major find, because here we've seen the same kind of outcrop we saw before, but not just 30 centimeters worth, but like 8 meters in a row. So they now have the water history spanning a much larger time scale from the outcrop in this crater. And we're trying to get to one 5 kilometers south that's even six times bigger. It may have even more history to show. But this is the kind of image that we would see. And this actually doesn't look all that bad. It looks like a flat plate of rock. It looks like you might be able to drive there pretty safely until you look at the whole context at the right angle. And this is about as far as we got. The science team really wanted to go a little bit farther to where there were intersecting strata, where you could see the lines intersecting at a point. But in order to go there, we would have had to risk slipping quite a bit along the way and getting stuck inside the crater forever, and they decided that wasn't worth it. So we got this far and then turned around and came back. And this is all the features it found using its visual odometry as of September last year. So since we left the crater, we drove by our heat shield. So this is the first time anyone got to see what the impact of a heat shield looked like on another planet. You might have seen in the news last year, we also got something impacting on Earth, the Genesis mission, sort of crumpled and broke open. But this is the first time we've had a chance to look up close at this material on Mars, and we spent a couple weeks looking at it here. Unfortunately, some of this dark stuff from the heat shield itself, and some of it got onto the rear hazcams. So now we have these speckles of dust on the rear cameras, but it's not so bad. You can tell in the sky, but you can't really tell on the ground images. Just to give you some idea for what our driving is going to be like for the next year, it's pretty much straight ahead. You can see Endurance Crater in the background. That's about half a kilometer away. And the tilt history here, landed in a crater, so we started a little bit higher tilt, drove on the plains, and then got into an even steeper crater here.
These tilts are forward, backwards, or to the side?
Overall. Roll and pitch are forward and sideways, and that's the overall tilt, whatever the angle is from up. So we landed more or less here, and we visited actually I guess this is Endurance, and we're driving south to Victoria Crater, if we can get that far, about 5 kilometers away. So that's about it. Just to summarize, when you go to Mars, you want mobility, okay? Because Spirit needed to drive 3 kilometers to get to the evidence they wanted. Opportunity's evidence was only 9 meters away, but just imagine landing without wheels and trying to see what's 9 meters away. So it was really good to design it as a mobile mission. We'd driven 5,000 meters as of that time. Now we're up to over 6,000 meters combined, and we'll probably hit over 10,000 total if things keep going well. We have some bonus capabilities, good position estimation. The autonomous navigation, when I wrote the software, I thought it was going to be used mostly as a safety feature for nearby drives, but it turned out they only used it to drive into places you couldn't tell how safe it was. So I'm very happy that it's working and kept us safe for now about 1,800 meters of driving through completely unseen terrain at that rate. And the visual odometry was actually extra credit. We managed to demonstrate that it could work, and they decided to go for it and add it in, and now we've been using it all the time when we're driving on these slopes. And that's it. Just to give you a quick overview, what's coming up next. Right now we have the Mars Exploration Rovers, Mars Odyssey and Global Surveyor in orbit. In 2 years, or actually this year, we'll launch the Mars Reconnaissance Orbiter. 2 years later, we're going to send another lander. This is basically reflying the Mars Polar Lander mission. So that mission was lost because of lack of integration testing. We think that it just turned off its thrusters too early and hit the surface. But we're going to fly it again with a different landing system. And 2009, hopefully we'll be sending another rover, an even bigger rover. And this one may even be nuclear powered. They're talking about giving it that kind of power, which will make it much more capable of exploring in more interesting areas. Our rovers, being solar powered, had to land near the equator and had to have a very wide landing ellipse where it was safe. And these ones would be able to go to much more interesting places. And sometime in the future, we may actually have a sample return mission. So that's it. Any questions? Yes?
I've heard that the dust that settles on the cells, that determines the lifespan of a mission. Does it? And if it does, do you guys do anything about it? Like, do you get rid of the dust and stuff?
Okay, so the question is, does the dust that collects on the solar panels determine the lifetime of the mission? And if so, what do we do about it? We thought that it might determine the lifetime, but so far we've been there for more than a year, and certainly we've lost some power to that, but we're still going very strong. We still have a lot of power left, still like 60% of what we had when we started.
So is that the determining factor? If everything else goes fine?
It's looking like for this mission that's not the determining factor. It's looking like for this one something else will break, like some motor will break or exceed its lifetime, get stuck, and that'll be what does us in. Opportunity actually had a very strange thing happen. It actually got a lot of power back. At some point a month or two ago, some of the dust seems to have collected and fallen off. And we don't know if that's due to frost or high winds or what, but we got about a 10% power boost one day, which was nice.
Yeah. In 2009 Mars Science Laboratory, what does it refer to? What are you going to have on board? What are you going to be testing for?
Okay, so what's in the 2009 Mars Science Laboratory? They're still putting the mission together. They only announced within the last 2 months what the science instruments will be. But basically, it's more instruments that are more geared toward life detection or evidence of past life. The Mars rovers right now are geared just to finding water history. Even the microscopic imager sees a 1 square inch image, but that's not enough to see the fine bacteria, for instance. So these will have higher resolution imagers and a zoom lens on one of the cameras and a different suite of science instruments that will be geared toward detecting evidence of past life.
Will they have enough to if you luck out again, have a conclusive result?
Well, is there enough to have a conclusive result? And I don't think we'll know that until we see the results. So we'll do the best we can. And obviously, it's always better to bring something back to Earth and use a Earth lab.
Are the instruments strong enough so that if you luck out, you could have a conclusive result? Or will you have to wait until you send back the sample from Mars in 2013?
I don't think that the instruments on MSL will be able to guarantee anything that, if there's something that was alive, we'll find it, because it could be any scale. It has to be designed to some limited resolution, and if it's below that resolution, we won't see it. So the best way to determine is to bring a sample back. But this will be the best we can do by going there. Yes?
Has it affected you at all personally to live with so much of your life at such a distance in time, like these time spans, to be planning missions so far out in time and to, have your attention directed so far away?
Okay, has it affected me to be living on this time scale where you're planning things years into the future?
And at such a distance. I mean, your life is up there.
Yeah, and while my life is up there, when I go to when I go to work, I sit down and I look at the latest pictures from Mars and I see if it's safe to drive. And sometimes I even get to command the rover and tell it where to go. It is a change. It was actually interesting during the first part of the mission, the first 3 months. We all lived on Mars time, not on Earth time, which has an extra 40 minutes in a day. And, companies would love that, right? Get more work out of you. But for me, it was actually nice. I somehow, my body felt more in the groove with that. I got more sleep doing that. I felt I got more done. And there's no traffic, right? You get, you're leaving for work at different times during the day. Probably the worst thing about it was that before we landed, the project manager gave a talk, a team morale talk, and introduced the head of the lab and said, "And now here's Charles to tell you all about the free ice cream." He's just kidding. But 2 weeks later, we had free ice cream. So for 3 months, I had free ice cream, which is very, very bad for me personally. But no, it's been great for me because I was inspired when I was a kid by all the space missions and the Viking missions exploring Mars. So it's been amazing to be part of the next one that actually gets to see even more and go even farther.
Thanks very much. And if there are more comments.